Okay, stats students, let's see if this video is a little bit better. Hopefully we won't have as many interruptions. We're going to go ahead and work on section 1.1b, which is really breaking down how to work with categorical data. And so when we're working with categorical data, a really good way to kind of display or just organize your information is with a table. And so it's really nice to quickly and efficiently organize that data. We'll be working with two types of tables. There's the frequency table, which could also be kind of a tally table, where you're really just displaying the category and then how many different people fit in that category. So really your number of individuals that fall in that category. The relative frequency table takes that data and turns the numbers into percentages or proportions. So when we're looking below, we have the distribution of bachelor's degrees awarded in 2007. So we've got two different tables. And my first question to you is, this is definitely categorical because we've got some words describing the categories, but what is the variable? What are these words talking about? What are they describing? And this kind of goes into here. They're talking about the major and the major for each of the bachelor's degrees in 2007. So the variable being measured is a major for each bachelor degree in 2007. Now this may be for a specific school or it may be for a state. They don't give us that information, but at least we can identify what this information is. Now one of these tables is a frequency table and the other one is a relative frequency table. Which one's the first one? The first one is a frequency table because we're looking at the number of people or the number of individuals that fall into each major, each category. So that means the second one is a relative frequency. And we could tell because it tells us the percent. So a lot of times we work with percentages, especially when we have such big numbers, so that we can look at kind of like the whole picture. What's the breakup? Where do we see the most people going into? And so it helps us figure out how everything relates to each other, and that's how it becomes a relative frequency table, because we see the relationships between them. Now, when working with a relative frequency table, every time you turn anything into a percentage, you're going to get some funky decimals, and so we tend to round them. And so we'll also get a rounding error. So you may see that percentages don't add up to 100 or add up more than 100. That doesn't look right. Don't. And so you've got to be a little bit careful about that, but also be aware that it doesn't really mean you made a mistake. It's just a simple rounding error that just comes from the nature of we can't process, we can't work with numbers. Like, we don't really need to know that it's 27.2853%. The 27% will be just fine. We can wrap our brains around that. But the extra part, it's not really going to make much of a difference for us. So this rounding error really isn't a mistake as much as it's extra information that isn't hugely relevant at this point in time. Now, when discussed earlier about how relative frequency tables can have percentages, which we're kind of used to working with. That's just naturally how we think, versus proportions. Now, proportions are the decimal version of a percent. So 55% as a proportion is 0.55. Now in stats, we're going to try and stick with the proportion. This is what we want to have. Because mathematically, if we need to do anything with that, mathematically calculate it, we can only calculate in proportion form. We can't actually calculate in percentage form. But percentage form makes sense to the general population. So they like to hear things as percentages. But mathematically, if we're going to do anything with that, we need to use proportions. So we're going to keep our stuff as proportions. Okay, now when we graph our categorical data, most of our graphs are going to be bar graphs. And the bar graph is going to illustrate the distribution of the variable. And so remember, distribution, it tells you, and then categorical data is like, what percentage of the people are in this category, what percentage is in this category, what percentage is in this category. So you get an idea of what everything kind of looks like. You're looking for patterns, you're looking for anything that's occurring. Bar graphs can also be bar charts and are used only for categorical data, not for quantitative. There's a different type of graph for that. Bar graphs can be used with counts. So you could actually use frequencies, or you could use relative frequencies. For comparison purposes between different groups of data, so you may do a bar graph for females, and you may do a bar graph for males. And so you're looking at favorite color for females and favorite color for males. And if you want to compare them, if you have different totals for the groups, it's better to compare in proportion or percentage form. So we try and keep to that, mainly because it's just better for us to really wrap our heads around and really see what's happening. Because it's no fair if you have a group of 10,000 females that you're going to compare to a group of 500 males. So when you're looking at just numbers, it's going to look outrageous for females, and that's just because you have a higher total. When you look at percentages, those total numbers don't matter. You're saying a percentage of this group versus a percentage of that group. So your groups don't have to be the same size. So when you're making bar graphs, it's really important that you're labeling your diagrams with the variable that's being measured. Everything needs to be labeled, because you may be able to tell, oh, well, this is for this and this is for that. But anyone else who looks at it is all like, that's group I? What's I stand for? And so without all that extra information, they don't really get it. And then decide if you're going to go with a frequency or relative frequency, and make sure you're labeling your axis appropriately. So if it's a count, label it as a count. So number of people, or number of zebras. If it's a proportion, label it as a proportion. If it's a percentage, label it as a percentage, so we understand what that actually means. So we have 15 to 18-year-olds that own personal media devices according to the Kaiser Family Foundation. And we're going to go ahead and we're going to make a bar graph. So we have 85% of 15 to 18-year-olds own a cell phone, 83 MP3 player, 41 handheld video game player, 38% laptop, 20% portable CD tape player. Since they gave it as percentage, I'm going to go ahead and make my table as percentage. So I label percent. And then I'm going to go ahead and divvy up those percentages. So this will be 10%, 20, 30, 40, 50, 60. And you need to make sure that your axes are consistent and fully labeled. And then we're going to go ahead and create our bar. So we're going to have a cell phone. So I'm going to go ahead and make a bar for cell phone. And I label it fully. And since 85% had cell phones, I make my bar so it's about 85%. Now I made my bar 2 units wide, so now every other bar that I make needs to be 2 units wide. So now if I do MP3 player, and with bar graphs there's spaces in between them. So MP3 player, 83%. Try to make it a little bit nicer than mine. And then handheld video game player was 41%. And then laptop was 38%. So you kind of get the idea. But it doesn't mean I'm going to stop. I don't leave it incomplete. And then CD tape player, 20%. You can tell this is from my generation because people would still own tape players. And so it really allows you to analyze to see that most people have the newer technology. Your cell phone, MP3 player, especially nowadays, not as many people having laptops, maybe because they're more expensive, but also because our cell phones are almost as good as laptops anymore. Okay, so I have the thing up there again, and really because I want to talk about another type of categorical graph, which is the pie chart. And they will not be on the AP exam. But they're used all the time in media. Most people use pie charts because people can just look at them and they kind of get the idea. Pie charts are not appropriate if you don't have all passable categories. So if you have some categories that really just don't even add up to 1%, you could have an other category and pile those all together. So that way every single option is kind of illustrated. And you have to be careful that it represents kind of the whole picture. And so when I'm looking at these things, for a whole picture, everything would have to add up to 100%. And when I look at these percentages, they don't add up to 100%. And the reason why is because people can own more than one device. So for a pie chart, you have to make sure that each person is in one category only. And so you have to be really careful about how you're doing that. So this data is not appropriate for a pie chart because individuals could own more than one device. And the percentages don't add up to 100 or close to 100. Okay, sorry about that interruption. So we're kind of back. So the percentages do not add up to 100, so that makes it not good for a pie chart. So when you're looking at graphs, there are some things that you really want to stay away from that unfortunately we see in the media all the time that makes graphs bad. And so one of them that I kind of talked about before is that the width on your bars need to be the same. Because our eyes register the area represented by our bar, and that's why we shade them in to get a really good idea of what's happening. And so if you have a different width on the bottom, your eye is registering a bigger area for the wider ones and a smaller area for the not as wide ones. And so it exaggerates the difference between them, and we don't want that. Using pictures instead of bars. And this kind of goes back to the area, because as you enlarge a picture and stuff like that, again, it usually grows up and out. So it's increasing 2 dimensions and it's making it a bigger area, and it's really not proportional to the area you're trying to illustrate. And then a big no-no is leaving off the bottom of the scale. So typically you'll see that as your scale will start at 20,000 here and then go up. And so your bar may look like this and like this and then like this. And it makes it look like there's a huge difference, when really, if you were to go all the way down to like 0, your bars would look like this and this and this, which, because you've cut out all this part down here, it exaggerates the differences between those two. And that's not appropriate. And it brings us into a big point that I see all the time in the media, and I'm always asking the questions like, how was that study designed? What's going on here? And that's something that we're trying to teach you in this class. We don't necessarily expect everyone to go into statistics and run all these tests and go into research, but we do expect you to learn how to be good at spotting, is this real information? Or is what they're telling me true? Or is it them just kind of trying to get me all excited and buy their product or get on their bandwagon? And so there's kind of this idea of statistics themselves don't lie, but people will twist them around or omit information and lie to you with statistics. And it happens everywhere. So we'll continue on with categorical data tomorrow.